Okay, let's go ahead and get started. So first off, I want to thank you all for coming. My name is David Lindsay. I am going to be talking today about how you can level up your development skills with static analysis. So I'm going to start out by talking a little bit about who I am, what my background is, who I work for, just so that, be fully transparent on that front. I'm going to talk a bit about what static analysis actually is. I imagine there's a good number of you who are actually doing static analysis already to some degree, but I'll talk a little bit about what it is, what makes static analysis hard, and what are some of the things we can do to make it easier to do, and what the difference is between a shallow analysis tool versus a really deep analysis tool. I'm also going to talk a little bit about why it's important to actually do testing, in particular static analysis testing, and also then go over some real-world examples of things you can find with a deep analysis tool, a deep static analyzer. I'll try to leave a few 10 or 15 minutes at the end for questions, so feel free to save your questions for then. But if you have questions during my, if something's unclear, if you need me to slow down, feel free to raise your hand or interrupt. I'm fine with that too. So first off, like I said, my name's David Lindsay. I actually have a application security background. I graduated from university about 10 years ago, 12 years ago, and I studied mathematics at the time, and then I thought I was going to transition into a career as a developer, and so I started out from college by getting a job doing quality assurance, and it actually was a really good experience for me in that I was working hands-on with Java developers on a very interesting Java project. But as I was doing the QA testing for this big Java web application, one of the things that I noticed was that it had a lot of interesting security issues, and at the time security was a new thing to me, and I started, and since nobody else at this organization was responsible for application security, I kind of took it upon myself to start researching and doing more on the application security side. And I started researching things like cross-site scripting, and then I would go and test the application for cross-site scripting, and sure enough, it was vulnerable to cross-site scripting. And so I'd test for something else like SQL injection, and it was vulnerable to that. So it actually was a really good training for me to get into a lot of these really interesting but very critical security type of vulnerabilities. And so rather than ending up going from QA to a developer career, I ended up going to a consulting firm after that and doing security consulting. So over the last 10 years, I've worked a lot with developers and engineers and architects for applications on how they can make their applications more secure. But I think it's really key to focus on developers in many ways, because they're really at the heart of what's going on with any application. So that's kind of how I got into security testing. Most recently, I've been working as security product manager and evangelist for Coverity. Coverity was founded about 10 years ago as well. They started out, by a bunch of researchers at Stanford University who were looking at, difficult, challenging problems, and one of those, or a lot of those problems were related to static analysis. So they ended up forming the company Coverity. Initially, they focused a lot on C++ type of issues, which are by no means easy issues. They're some of the most difficult types of issues. They're things like integer overflows, buffer overflows, memory management issues. Fortunately, Java came along and made some of those types of problems go away, but other problems emerged as well. And so Coverity now does focuses on Java security as well, in particular web applications. So I'll talk a little bit about some of those details, but again, I'm not trying to, hype my company or focus too much on our particular products. I'd like this to be a very generic, just, focus on static analysis in general. So, I mentioned earlier how developers are really key to doing security well, and it's not just for security, it's for testing as well. And I like to think of one of the mantras of agile testing, in that it's useful to have short feedback loops, and by doing testing at the development stage is really one of the best ways to do that, because you have the shortest loop. In particular, security is oftentimes done after the fact, or an organization will have a security team that will test, an application right before production. And that's great to do, but it's not nearly as beneficial to an organization as if they were doing some of that testing and development. Now, there's lots of different types of, bugs in an application, including security bugs. Some of those can be found earlier on. Some of them can't be found until later on in the development lifecycle. So by all means, static analysis is not going to be your cure-all for everything. It should be part of a mature, testing program that any organization does. But it's also, one of the most key parts for people in this room, something that you can actually take on your plate and do. So just for clarity for anybody who maybe is new to the concept of static analysis, what exactly am I talking about? So I like to compare it, static, gets the word, static analysis gets the word static as opposed to dynamic. So I'll start out with talking a little bit about dynamic testing. Dynamic is, runtime testing. So you take an application, run it in a production environment, for example, and you can do testing there and find things. Like one common dynamic testing technique is to do penetration testing, which I used to do a lot of as a security pen tester. In this case, I would kind of play the role of the bad guy and see, okay, if this application was out there, how might I attack it? What kind of sensitive information does this application have? Does it deal with credit cards? Does it deal with, private healthcare information? Does it deal with, does it a shopping cart? Are there ways that, that the business logic of the application can be abused? For example, if there's a shopping cart, maybe I can, abuse the way coupons are applied to get things for free, or maybe I can, change, the value of my items so that instead of costing $5, it costs negative $5, things like that. And so I really, just take whatever the application has, focus in on those sensitive parts, and then see how it can be abused. All of that is done dynamically in that it's more kind of like testing a black box. I don't see what's going on under the hood. That all happens server side, and I don't have access to the source code normally. So static analysis is kind of flipping that around, and it's starting out with the source code and saying, okay, what kinds of things can I find by looking at the source code itself? And usually when we're talking about static analysis, it's not just lightweight grepping through the code. That certainly is useful, and you can use that as especially if you're doing a manual code review. But to do real static analysis usually involves going deeper and running sophisticated tools on the code to find interesting defects. And I'll talk a little bit later about some of those types of things. So one of the things I'd like to emphasize, though, is there's different levels of testing. I guess the best way to do that is to make an analogy with gaming, since that's kind of my theme here. So this is a really simple type of game or puzzle. Raise your hand if you're familiar with Sudokus. Hopefully most people. Okay, good. That's why I chose it, because it should be something that everybody relates to. I thought about using Minecraft or some other example, but I wasn't for sure if everybody was, super familiar with those. But Sudokus are pretty basic, and this is the most basic one I could find. So, this is a really simple, Sudoku. If you want to step it up to the next level, this is a more traditional, classic kind of Sudoku. Probably most people in here have solved Sudokus like this. These are definitely challenging. Like, probably, I'm not the fastest at these, or this would probably take me a half hour to an hour to solve. They're fun to do. They're definitely, a lot more sophisticated than this, right? But then, there's even, a step beyond that. So there's Sudokus that are like that. I think they're called samurai Sudokus, or I'm sure there's other names. But, this is like a whole nother level of complexity of wow, I didn't even know that existed out there. And it's the same, it's the same with, tools like static analysis tools. There's really basic lightweight tools. There's more medium advanced tools. And then there's tools like this that are just completely on a different level in terms of complexity. So, I've talked about some of these techniques, some of these types of tools. Manual code review, for example, is one option you can do. And lint checkers, for example, are very useful to find certain shallow types of issues in the code. Unit testing is great type of testing, very narrow focus testing, but still a useful thing to do. There's static analysis testing, like I talked about, and dynamic testing, like I talked about. There's also, some newer techniques that are coming out, like runtime analysis, where you actually instrument the running code, and that helps you to find defects that way, or you can combine that with fuzzing techniques to identify certain types of vulnerabilities. I also talked a little bit about penetration testing. So, there's this whole range of things. But, for now, let's just focus on things that really apply to developers. And, things like dynamic and runtime testing are more things that like a security group is going to do. Same with penetration testing. A developer can really focus on, these types of things like unit testing and lint checkers and static analysis. And of these, static analysis is really where you get the most beefy, core, deep analysis. And so that's why I think that it really deserves extra consideration for everybody in this room as something that you can bring to your game that you might not be doing now. Or if you are doing to some degree, maybe you can start adopting other tools that take it up to the next level. So, in keeping this generic and not focusing on any particular tools, what are some of the things that you might want to consider if you are trying to decide on a good static analysis tool? Well, obviously you want to find defects, right? That's the whole point. But not just any defects. You want to focus on defects that really matter to you and to your organization. And that can be, obviously subjective. It can be hard to know what those things are, but a good tool will be able to understand your environment, be able to understand constructs in your code, and will be able to tailor those results to the things that it thinks you'll be interested in. There's also accuracy. I kind of mentioned it twice here because there's a couple different ways to think about that. One is you don't want to miss, important things. So if there's for example, a very critical, bug that causes your application to crash and the tool misses that, that's obviously a bad thing, right? We call those the false negatives. And so obviously you want to look for tools that keep those false negatives down to a minimum. There's also the other side of that, in that you don't want a tool to give you garbage. And I'm not just talking about garbage in terms of things that are actual findings but are not interesting findings, like you didn't indent properly here. I'm talking about just things that are flat out wrong. And there's a wide range there's a big spectrum of different tools in terms of false positives. Some tools, just by normal out of the box, will have about 95, 98% false positive rate. That's really, really high. That means, for every 100 issues that it reports, over 95 of those issues are going to be just completely wrong. Then there's other tools that have, a false positive rate around, 15 or 20%. For a developer that's looking at a static analysis tool, that's obviously where you want to focus on, are tools that are at that end of the spectrum, because no developer wants to waste their time with a tool that's going to report a lot of garbage. To be fair, the tools that do have really high false positive rates, they actually are useful still. Like as a penetration tester, when I would get a chance to look at source code, it was still better for me to take a very noisy tool, static analysis tool like that, and get the results, because that still saved me a lot of time over what my other options were. It still would be a lot faster than manually reviewing the code. And so even though it had so many false positives, I had the time and the expertise to go through and quickly figure out which ones were real issues and which ones were not real issues. And so there's still a value for these tools, but that value is really to somebody who is specialized in security or specialized in these types of issues. And for a developer, they probably want to stay away from that end of the spectrum, like I said, and focus on things that are going to be less noisy. And there's obviously a lot of other considerations as well, things like the ability to quickly triage an issue. By triage, I mean, when you do get a list of report of different defects, you have to decide if they're real or not, if they're true positives or false positives, and the triage is what mechanisms the tool gives you to make that decision quickly. So if you think about that, you maybe want to be able to view it, inline in your code, for example, so that you can quickly hone in on, the important parts of the defect to see if it's real or not. The other is just how quickly the tool runs out of the box, or runs on your application. If it's too slow, that obviously is not a great thing. I do have to say most static analysis tools do run on the slower side compared to other things. It's just the nature of the beast, in that if you want to do a really deep, thorough analysis, it is going to be a bit slower. But that being said, there's innovations being made all the time to still do a deep, thorough analysis, but maybe take shortcuts in some ways so that you can still get results quickly. Other things like customization, like no tool is going to be able to perfectly understand your code, so it's good to be able to write custom models or be able to inform the tool to some of the specifics on your code. So that's another thing to look for. I didn't want to list out everything, but I provided a link here for those that have the slides. so that you can, at the webappsec.org website here, people have put together a good list of, much more thorough and comprehensive evaluation criteria, things that you might also want to consider. Okay, so let's talk about, get a little bit deeper here on what goes on in the Java land when you're doing static analysis. So, a static analysis tool is really going to mirror, what goes on with the compiler in a lot of ways. And so, and a good tool is actually going to look at the compilation process. But that's one way to do it. The other way is to actually just look at the bytecode. And there's a couple of pros and cons to doing it both ways. So I'll first talk a little bit about, just doing bytecode only analysis. In this case, it can be really useful, especially if the code is, compiled with debugging information that allows you to, tie back to the source code. And it allows you to, just by focusing on the bytecode, you can still find a lot of interesting issues. However, when you look at just the bytecode, you're also sacrificing some fidelity in that you won't be able to go as deep in certain areas. And some things that are really transparent and obvious at the source code level will not be obvious at the bytecode level. Things like, access to config files and so forth. So, but that being said, one of the real positives to doing just bytecode analysis is that the actual source language is independent. Anything that compiles to the, to the bytecode can be analyzed, obviously. And so that's definitely one of the pluses to doing bytecode only analysis. The other option that I alluded to before was doing an actual, deep dive analysis on the source code and monitoring as it compiles. And that allows you to, like I said, to go a little bit deeper and find certain types of issues that you wouldn't find other ways. So in order to do this kind of deeper analysis on the source code, I'm describing a little bit about how the Coverity tool works, but this is pretty similar to a lot of other tools. So you want to monitor, whatever your build process is, but look for wherever Java C is being called and where code is being compiled, and make note of those, and kind of follow along with the build process. And the tools will typically, collect their own information as part of that and save it off somewhere so that it can be analyzed at a later step. So there are things like, as the code is compiled, an abstract syntax tree is built, or call graphs are built, things like that. And those are things that are that's the kind of level that a static analyzer will want to focus on in order to do its analysis later on. We'll talk a little bit later on about the actual analysis phase, but even before you get there, there's a lot of challenging things that must first be solved. And I mentioned a bit earlier, how one of the artifacts that you want to look at is the control flow graph, or the control flow graph. So this is an example of like a really simple case of how the control flow graph might look. In the real world, the control flow graph is going to be much more complicated, and doing the analysis on the control flow graph is an undecidable problem. It's akin to the halting problem. And so doing the analysis on the graph is going to be, the best we can do is come up with a good approximation of that. And that's just one of the things that we have to accept with static analysis. And because it's such a, for most applications, the control flow graph can be really large, and you have uncertainties about the actual, which connections are actually made in the graph. It means that you need to really have a lot of smart tuning in order to properly understand it. So I'm going to talk about just one or two ways you can actually, improve that, traversal and that understanding of the call graph. But just keep in mind that these are just a couple examples. There's hundreds of tricks and things that a static analysis engine will do in order to make these kind of improvements. So one example is just doing intelligent caching. So to illustrate that, imagine if you are traversing the call graph of an application, excuse me, the control flow graph. You might be traveling through different nodes, and say you go from A to B to D to E to G. So that's just following down the left side here, right? And then later on, you'd maybe unwind and go back to state A, and then you'll traverse it through the other way where, the variable now from, instead of being true, is now false, and you'll go from A to C to D, and then again, you have two paths. You can go here, E to G or F to G. But the second time we go through this, going from A to C to D, once we get to that point D, if we're smart, we can stop there and just look at the cache information because if we're able to, at that point D, to say, yes, we've been here before, I know what's beyond here because I'd already traversed it, once before on a different branch. And if I know that true-false variable earlier does not affect, what's going on after D, then I can say, okay, going beyond this point is unnecessary. And so that's just one example of how you can, employ caching techniques, for example, to speed up your analysis and your traversal of the call graph, or excuse me, the control flow graph. Another technique that's used is to, create what we call summary methods of different blocks of code. And by, the summaries are basically kind of abstract, or higher level, descriptions of what goes on within a particular block of code. And that allows you to more quickly, parse and understand those blocks of code, which speeds up things. So I don't want to go too much into detail on all of these because it really takes, a lot of, deep understanding and theory that goes on under the hood in terms of how some of these techniques work. But if you are interested, I'm happy to discuss afterwards. And, my colleague, one of our head researchers, is here in the audience as well. I'm sure he'd be happy to discuss some of these as well. But I do want to talk a little bit about some of the categories that you end up with. So there's, at the end of the day, when you do the static analysis, the types of findings that you get kind of fall into different categories. So a couple of the main ones are called interprocedural findings and the intra-procedural findings. So the interprocedural findings are going to be the ones that are just specific to a particular method or block of code. And then the intra-procedural findings are going to be ones that kind of span across multiple parts of the code and require, that really require that deeper understanding of how different parts of the application are connected. Kind of related to that, but somewhat different, is called data flow analysis. And this part, instead of just looking, what parts of the code call other parts, you're going to look at how data is passed around in the application. And this is important, especially for a lot of security issues, because a lot of security defects, especially in Java applications, fall into this category of data flow type of findings, or and so a solid data flow analysis can really help you do this. So just want to talk a little bit more about the data flow because I'm going to give some examples later of this. So when we're talking about data flow, there's a couple key words that you want to keep in mind, and that's source and sink. So like I said, data flow analysis is looking at how is looking at how data flows through your code. And so what a source is going to be anywhere where you have external data come into your application. Now, external can mean lots of things for different applications, but let's keep it simple and just think about like a server, a web server application, or application running on a web server. So, anything that is submitted from the user, for example, would be considered a source, because that is data that's coming in from outside your application. It's not trusted, right? For, if you want to keep a more concrete example, think of just like a login process where the user submits their username and password. Both of those are untrusted bits of data that come into your application. So that's the source where this untrusted data comes in. And then it's going to, traverse through your application in different places. It's going to get saved to a variable. It's going to get concatenated with other strings. It's going to be, manipulated in different ways. And then it's going to, end up somewhere. And there's lots of different places where that, untrusted data can end up. It could get, sent back out to the user. For example, if, this is a failed login attempt, it could say, David, you need to log in again, or you need to try your credentials again. If it has something I entered that gets that untrusted data gets put back out on the page, that's what we call a sink. So that's one example where of a sink. Another example would be if my credentials are being used to make a query to the database to see if I actually am an authenticated user. So in that case, my username and password are maybe getting put into a SQL query, and that SQL query is getting executed against the database. Well, when that execute happens, that's what we would call a sink, because now it's being, sent, that username and password, this untrusted data, is being used in a potentially vulnerable way. So there's lots of different sinks that you can come up with. For example, writing to, if a string is being used to write to the file system or to execute a command or to load external resources or to make an LDAP query or to build a regular expression, all of these are different, types of sinks that you could have in your application. And an attacker who is able to, identify these types of sinks is going to be able to flag these as, security issue or as a security problem in your application and quite likely come up with an exploit that somehow takes advantage of it. And again, I'll give a couple more detailed examples of these in a second. So before I move on, though, I wanted to go back to this slide just to talk about one other type of analysis checker that we have, and that's doing statistical analysis. So it's really, I shouldn't say easy, but if you have good pattern matching as you do the analysis of the application, then you're able to find certain constructs in the code that are similar to each other. And if you can identify similar parts of the code, then you can identify whenever there's a variation from that pattern. So things like, if you check the return value for null in 19 out of 20 cases, but that 20th time you didn't, that can be a good indication that you left something out. So this is, again, another type of analysis technique that can lead to very interesting vulnerabilities. And I'll give a couple of good examples of those in a minute as well. There's a lot of different types of issues that can be found at the end of the day using static analysis. I've listed up here in really small font, unfortunately, several of the types of vulnerabilities. Just to highlight a few, like I like to focus on the security ones since I have a security background, but things like security misconfiguration, exposure of sensitive data, cross-site scripting, path traversal, command injection, cross-site request forgery. A lot of these issues that are in this security category here are the data flow type of issues that we were just talking about. And there's also things like resource leaks, where database connection is not properly released, for example. And again, lots and lots of other types of things as well. It's interesting, in observing a lot of applications, it seems that about, it follows the 80-20 rule in that, 80% of the defects that are found by just, 20% of the checkers. It's not true for every application, but that, as a general pattern seems to hold. And so let's kind of focus on just some of those types of checkers that do tend to produce well, that do find a lot of vulnerabilities. One of these for Java applications is just, doing no reference checks. So I just have a simple little, a block of code here. But if you're checking, the variable x here to make sure that it's not null, and then you do something with it, then later on in your code you use that same variable x without checking for null, that is a really good indication that you just left out that null check, right? And so, and that can happen in either order, where you do the check first or you do the check after. But, in either case, this is a really, kind of classical example of something that can be found. And these types of mistakes are very, very prevalent in Java applications. Another really common one is different kinds of resource leaks. Creating Java, normally for a lot of different types of objects, it does a really good job at, like for any kind of constructor, for any type of constructor in the application, the destructor is called as well, and all that happens, seamlessly without you getting involved. But for, any kind of external resource or system resources, you have to manually do that still. So, like if you're opening a database connection, obviously you need to close that connection at some point. And for really simple applications, it's probably just not too important, or it's really easy just to not miss that. But for more complicated applications, especially when when lots of users are working on the same code base, it can get kind of messy, and oftentimes these things get overlooked. So again, this is another very common issue that's found in Java applications. Another potentially bad thing that can happen in an application is to have threading issues. And so we talked just a minute ago about the statistical checker and how we can identify, if you do something certain, one way, and then later on you do it a different way, we can, flag that using statistical checks. And kind of looking for, missing locks on your code is is one place where this is applicable. So if you, for example, always lock an object before using it, 15 out of 16 times, but that one time you forgot to do that, this is something we can easily pick out, assuming that we, can do the good pattern matching to begin with. Another really interesting class of issues that kind of is similar to the statistical issues I talked about is when when a developer cuts and pastes code. This is actually one of our newer checkers, and I actually don't know of a lot of other static analysis tools that do this, but it's really, really useful in that it just finds a lot of cool things that a developer missed. So these aren't necessarily going to be security issues, but in most cases it's really, once the issue is pointed out to a developer, it's really obvious that, yeah, I just, I cut and paste that code and I, had to substitute some variable, but I missed it in one spot. So if you look at, this example here, this is an example of where code was cut and paste, but something was overlooked. Has anybody spotted what was missed yet? Has anybody been looking at it? Sorry, speak up. Yeah, the last line, I can highlight it here. There we go. Yeah, so the last line was cut and pasted along with everything else, but instead of substituting the last word returns, they just left it as is. So it probably should have been r.locals.ast equals locals instead of equals returns. Does that make sense? So again, once it's pointed out to you, it's really obvious, but just looking at it like this, especially if this is code you just written and you just did the copy paste, it's really, really easy to miss things like this. So just as another example, spend just a second looking at this, seeing if you can spot what was, so if you can tell, like there's the if statement, and then later on there's another if statement, and so the following 3 lines after this statement are all kind of cut and pasted along with the if statement. So can you see, what was maybe missed when they did that cut paste? Yeah, so right in the middle, the check here in the if statement. Oh, is my pointer going to work? Yep. So the check here in the first one was if default value, and then something, and then later on it's else if, and then it's the same variable. So default value here is default value here. So down here, doing that pattern matching, we can say, oh, they actually didn't follow the pattern properly. So this variable here is different than this variable, whereas above it was the same. So we can pick up on that as a difference and say, hey, did you really mean to do this, or is this something that's a mistake? And in this case, it's something that the developer missed, something that was unintentional by the developer. So, I attended DevOps conference a few months ago in Belgium, and I've talked with developers at this conference, and I like to find out what kind of tools that developers use, and find bugs, for example, is one of the most common tools out there. I read what was that? Relics Lab had a survey from 2014 that talked about some of the most popular static analysis tools, and I think FindBugs was one of the top ones. Like 55% of all developers they interviewed were using FindBugs. And so I wanted to talk a little bit specifically about FindBugs because I bet at least half the people in this room have used it or are using it on an ongoing basis. So first off, FindBugs is a great tool. If you're using it, by all means, continue using it. But I just want you to know, you should be aware of what you're getting with, a tool like FindBugs. So on the plus side, it's free. So you can't go wrong with that. And open source tools are great. I have no, I'm definitely, a proud user of open source tools myself. On the other hand, it's just not going to be as enterprise worthy and as deep as some of the other tools that are out there on the market. And so, the types of analysis techniques that it's able to do, it does okay in some categories, but it just doesn't even attempt to do others. Or if it does attempt to do some of these others, it doesn't do a great job on them. So by all means, I'm not trying to knock on FindBugs too much, but if you are using it, just keep in mind that it's probably missing a lot of important things. So we did a kind of just a comparison, on a particular application, just to see how, the types of things that it found versus what our tool Coverity finds, just as an example. And there was some overlap, there are, but at the end of the day, I was kind of surprised at how small the overlap was. But breaking it out, the findings into different categories. The FindBugs found, a lot more issues than our Coverity tool did, for example. Altogether, if you add these up, 980 issues versus 266. So, if you just were naively looking at these results, you could say, wow, I'm like at least 80% of the way there just by running FindBugs. And, that other 20%, yeah, I can live without. But that's, if you tell yourself that, you're really missing kind of the key thing here, because not all bugs are created equal. Like we just talked about, some defects are a lot more severe or important or critical than other issues, and that's really all along the types of issues that the Coverity tool has focused on. And so even though you maybe are getting 80% of all your findings just by using find bugs, you're probably missing a lot of the really important key things that you should be looking for. So, for example, us at Coverity, can we do better? Definitely. I don't want to say that we are the greatest thing to ever come along. We're always looking to make improvements, and these I just wanted to highlight are some of the things we're looking at right now as future improvements to our tool. We want to do a better job understanding mobile applications. We want to expand it to supporting additional languages beyond just C, C++, Java, and C#. There's a lot of scripting languages out there, and it turns out they are a lot different than languages like Java and .NET. And so to do a really good analysis on a language like JavaScript or Python, we just have to kind of start from square one in a lot of ways in terms of building up a thorough, deep analysis engine. So that's one area we are looking at. And then we're always looking at ways to better understand frameworks so that we can eliminate false positives and find more of the false negatives and so forth. So I do want to give a demonstration just so you can see a little bit about how the Coverity tool works. It's not the most interesting demonstration, but there's there's a plus side to that too, in that it's a very handy tool still. So one of the things I like about the Coverity tool is that it's all command line driven, and so that's kind of what makes it less interesting. But it also makes it very powerful for developers in that they can easily build it into their workflow. So let me just show you real quick how that might work. So I have here, kind of a sample application. It builds using Maven. And so if I were to build this application on my own using Maven from the command line, it would just be this one-step Maven clean package. But to add in the Coverity analysis to that build process so that the Coverity tool can understand what's going on, I just have to kind of wrap it with this cov build step. And the only command line argument I'm passing in is the --dir, which is going to be where Coverity tool will store off all of its artifacts as it's doing the analysis, things related to the call graph and control flow and so forth. So let me get that going. And the other reason I wanted to show this is just to show how quick it is. And so I'm going to do the build here, and it will be done in just a couple more seconds. So again, this is a small project, but still, this part of the analysis is actually fairly quick. As a second step, for web applications, I can analyze any EAR files or WAR files that come out. So I'm going to do that as a second step here using cov emit Java. And rather than specify the WAR file that was just built directly, I'm just going to have it find it on its own since it's smart like that. And again, this will just take a couple seconds. So right now it's going through the JSPs and compiling them and looking for, like we talked about data flow earlier. So right now it's looking for sources and sinks in the code and things where untrusted data is coming into the JSP. And again, that step's already done. And then the third step here, just got to scroll up to my text file, is just going to be we call it cov analyze. So I'm just going to, again, specify that directory where the Coverity tool stores off all of its findings and make sure that it's going to include any of the web application security issues as a command line argument. And this will probably take a minute or two. So while that's going, let's kind of skip ahead and see some of the actual findings that you might find. So once the cov analyze tool has finished, it will store off any findings that it has, and then the last step, which I'm going to leave out for now, is just to commit those to a database, which then can be viewed by this web application. So this web application is the tool that Coverity provides to developers to quickly see what findings were found and view and to see the findings and to do triage on them to quickly determine if these are real issues or not. And we do that by trying to make it kind of like an IDE, so you can quickly skip around in the code. I'm going to just give a couple quick, easy examples here for the sake of time. So the first issue I wanted to show is a SQL injection issue. So again, going back to data flow, this is a case where untrusted user is coming in. So let's go back to the source here. Let's hope my internet connection's working. Oh, it might not be working on me. That's a shame. Okay, so okay, we'll do without skipping around. So you might not be able to see it as well now, but here in the background was where the untrusted data was being written to a SQL statement. So in this case, the untrusted data is being added to a variable called user, and that's being used in this query select star from user data, where last name equals whatever that untrusted data is. And between where that untrusted data came in and where it's being used here, there was no sanitization being used on that string, nothing to do to make it safe for being written to a SQL query. And so that makes it, really easy to flag as a SQL injection issue. So I'm going to avoid clicking for the rest of these. But let's look at another example. In this case, it will be like a SQL injection, or excuse me, a cross-site scripting issue. So in this case, the untrusted data is coming in here just using request.get parameter, and it's being stored to the name to the variable search name, and then just scrolling down a bit in the code, only a couple lines really, and that untrusted data here is being written out using JSP syntax to a message to the user saying that the person that they were searching for was not found. And again, between where this string search name is coming in and where it's being written back out to the user, between the source and the sink, there is no sanitization going on. So again, this is a case where it's a very classic example of cross-site scripting. In cross-site scripting issues like this, where the distance between the source and sink is only 2 hops, that's obviously a trivial example. It's not uncommon to find in more complicated applications examples where that distance between source and sink is 30 hops or more, in which case it obviously takes a much more deeper and robust understanding of the code to analyze. But since my internet connection's not great, it looks like I'm going to have to pass showing you one of the more complex examples. So another example that I wanted to show one that at least isn't data flow related, and that's just a really trivial example, but one where the static analysis tool is flagging where you're using a outdated cryptographic routine. In this case, the MD5 hash function. If you haven't been following any cryptographic news for the last 10 years, then you might not know that MD5 is dead, but really nobody should be using it at this point. There's no good reason for it, especially when it's so easy to just replace ththese 3 characters with SHA-1 or something, and you can be having a much more secure. Even SHA-1 has its issues, so I shouldn't go hyping SHA-1, but regardless, this is something that's pretty easy to flag using a static analysis tool, and so that's something that obviously you might want to fix. And the other reason I wanted to highlight this is because a lot of organizations have their own internally built secure coding rules, and so the checker that we have for this is something that can easily be customized to match with whatever that policy you might have. So for example, if your organization's policy is to never use MD5 and never use SHA-1 and to always salt your passwords before you hash them for the database, all of those are things that can be customized and enforced if needed in a really straightforward manner. Let's see, I think I have one more issue queued up here. So the last one is, just an example of command injection. So this is a case where, again, I won't be able to go back to the source, but you have untrusted data that's coming in to the application, and it's getting passed into the string variable here to this method, exec results, and it does some preparation, and then runs, calls runtime.get runtime.exec, and then on that command. And so again, if there's no sanitization between that source and the sink, this is where you have a classic example of where remote command injection is possible. So if you put on your attackers, or you put on your Blackhat and think, how can this be exploited? Well, an attacker, by exploiting this, isn't necessarily going to compromise your application, but they're actually going to compromise the server it's running on, quite likely. And in this case, would maybe get root access on the server, which would then allow them to further use this as a launching point to attack other systems within your corporate network. Obviously, that's something nobody wants to have happen. So, it's good to always, I think back and kind of play the devil's advocate, or put on your black hat and think about how these things can be exploited, because at the end of the day, some of these issues really are quite severe and can have really drastic negative effects if they were to be found and exploited in a production application. Let me skip through, because I was able to show these in the browser. Okay, so last part here. So I just want to, close up by, re-emphasizing why it is we do static analysis, or even testing in general. Maurice Wilkes, who helped, build one of the first ever computers, mentioned, I'll read just part of this. As soon as we started programming, we found out to our surprise that it wasn't easy to get programs right as we had thought. Debugging had to be discovered. I remembered the exact instant when I realized that a large part of my life from then on was going to be spent in finding mistakes in my own programs. So, at the end of the day, it's, writing code is hard, but, writing good code is even harder. And that's one of the reasons why static analysis tools can really help with that. Just as a quick example here, my wife, she likes to write poems and write short stories and books, and she spends days and days refining just a single paragraph to get it just right. And then oftentimes when she feels like it's in a good state, she'll bring it to me and be like, hey, can you review this? And that's not because I'm great at literature, or I'm great at understanding English and grammar. I'm actually quite the opposite. I'm horrible at it. But just the fact that I am different from her, I am a fresh set of eyeballs that are looking at it, I can easily spot things that she's overlooked, like a word that's repeated twice in a sentence, or something that's, a word that's left out. Those things are really easy when I'm looking at it with a fresh set of eyes. And it's kind of the same when you have, a third-party tool look at your code. It's just going to find things that are really, maybe in hindsight are obvious, but that you're just going to miss. You're not going to find. And so by having a good, static analysis tool that you can run on your code on a continuous basis is one of the best ways that you'll be able to find these types of issues. And at the end of the day, you'll actually become a better programmer as a result of it. Especially when it's something that you're going to be using on a day-to-day basis and constantly looking at the results, you'll actually start finding, like, learning about, these bad patterns or these things that you shouldn't be doing, and your code quality will increase as a result of it. So, at the end of the day, going back to the gaming examples, life isn't really a competition on who can get the highest score, but on the other hand, we all want to kind of do our own personal best when it comes to, improving our skills and our worth as a coder. And so, static analysis is, one tool that can make a big impact in helping you level up your skills and make yourself a better programmer. So, thank you. Any questions? We do have a free trial version that is available right now, so you can do an analysis in our cloud for free. But normally it is a paid tool, yes. What was that? On your cloud. On what? On your cloud. On our cloud, yes. That is the one limitation, yes. And so, any other questions? I have a hard time seeing with the lights. Yes? Detecting infinite loops, which is close to the halting problem. So the question being?
Normally the halting problem is
undecidable?
Yeah, undecidable problem. So normally you cannot solve it, but in some of the slides you claim that you can detect an infinite loop.
So in general, it is an undecidable problem. That doesn't mean that in certain cases you can't flag that an infinite loop is possible, for example. So it's just the difference between a specific instance versus solving it in the general case. Any other questions? No? Okay, one more.
Do you think the issue is finded is mostly related to the artwork or to the analyzers that are provided with it?
I'm sorry, can you speak up?
Do you think the issue is finded is rather related to UME?
With the find bugs, the analyzer is what?
Is rather related to the artwork, to the fact that it's bytecode something?
Oh, to the approach that it's bytecode analysis?
Or to the fact that, or to the analyzers that are provided with it, more specific.
Okay, So if I understand your question correctly, and do correct me if I'm wrong, I mentioned some of the limitations of the find bug analyzer, and the question is, are those limitations inherent to the fact that it's doing bytecode analysis, or is it for other reasons?
Or is it the specific analyzers that are provided with find bug?
Right. So I would say it's a combination of both. I think that even if it was just sticking with bytecode analysis, find bugs could do a deeper, better job in some areas. And again, I don't want to criticize any developers that work on find bugs. It's certainly a very useful, great tool. But there are a lot of the things that it do could be a lot deeper or be better. And I think that just is a result of the fact that a lot of these static analysis problems really are difficult, and there's been countless man hours of research and development that has gone into the Coverity tool, for example, and the same with other commercial tools on the market. There really is a huge difference in quality between the commercial tools and some of the free tools. Now, that's obviously not the case in all categories, but at least with static analysis tools, the way things are right now, that's the case. So. Okay, if you have any other questions, just come up and I'll be happy to chat with you afterwards. Thank you again.